at the most basic level, the problem that we're trying to solve with various configurations of computer memory is that we've got a processor over here that actually does all the work with things that are in registers, and we've got a disk over here that holds all of our information. Reads from the disk to the processor are really slow. So registers, really fast, disk, really slow. Registers are thousands, tens to hundreds of thousands of times faster than disk. So if we just had a program sitting there on a disk and we tried to run them in the processor, each time we got a new instruction for the program, we'd have to wait thousands, tens of thousands, hundreds of thousands of instructions before we could get, or cycles before we could get to the next instruction. So your computer would spend most of its time waiting. So, one thing to keep in mind here before we really start talking about memory is this idea of locality. So if you think about your programs, most of your programs spend most of their time in any given time slice accessing data that's pretty close together, both instructions and data. So if you think about the code that you write, usually you're writing a loop or you're doing things within a procedure or you're doing something that is operating on a certain set of data, usually in some sort of iterative way or a serial way, but it's accessing code that's close together. So if you map that all the way down to the way the assembly language is written, you've got a fairly, in any given space of time, you've got a fairly small space of memory that you're actually working with at any given time. So that small set of memory is called a working set. And the idea of caches and memory in general is that you're trying to take a really big total program and get as much of the working set as possible into as fast of memory as possible. So the way that we generally do that is with various levels of caching. So people usually think of things, if you're familiar with a processor, you'll have heard about like an L1 cache and an L2 cache and an L3 cache. Really RAM is also part of that caching mechanism. So you've got, again, a lot of data that's on a disk. So the first layer of that is RAM, and then the next layers are what are traditionally considered your caches. So the reason that you have multiple layers of caching is that as you move from the processor out to the disk, you have bigger spaces, you've got slower spaces, and you've got cheaper spaces. So I haven't drawn these to scale, they're all drawn at about the same size, but your L2 cache is going to be bigger than your register set, but a lot smaller than your L2 cache. And your L2 cache is going to be smaller than your L3 cache, and your L3 cache is going to be smaller than the RAM, and your RAM is going to be a lot smaller than your disk. So as you run your program, you're pulling things from the slowest space possible through your caching system to a place where it's in the fastest place possible to access, which really technically is the registers. But L1 cache runs generally about as fast as your registers run. So the trick to all of this is basically to make sure that you've got caches that are big enough to hold a reasonable working set for you in order to get things to you quickly. So we'll talk a little bit about how caches are laid out. Caches are basically associative arrays. And what that means is that any given piece, a cache is kind of laid out like a table. So when you read a piece of memory in, you map that memory address, and it's like a key value store. So the memory address is the key, and the stuff that's in that memory address is the value. The way that most caches are set up is that instead of reading one byte at a time in, they store a number of bytes in what's called a cache line. So again, that gets back to that locality idea. When you use a piece of data, you're probably pretty quickly going to need to use data that's related to that. So usually what caches will do is they'll basically break the address of a piece of data up into what's called a tag and an index. So the way the cache works is a simple cache, the way that a simple cache would work is that you would have indexes 0 through F, for example, if you were using 4 bits for indexes. And those would come from this second lowest 4 bits of your address. So when you put something in the cache, the only place where you could put this address would be in this index A. You'd then tag it saying that it's 0A is the upper part of the address. And then you'd store all the data from 0AAC all the way down to 0AAF in that cache line. So now you have access to all of it. So the first time that a program needs access to that data, it'll go out, it'll see if it's in the L1 cache. If it's not, it'll look in the L2 cache. If it's not, it'll look in the L3 cache. If it's not, it'll look in RAM. If it's not there, it'll finally hit the disk and pull that data out, bring it all the way back through, get it into the register, store it in these caches, so that the next time that it needs that information, it'll be able to look it up and it'll find it in the cache. The reason things are arranged in this index sort of system is that this makes lookups a lot easier. If you just had, so the kind of ideal cache is what's called a fully associative array, which means that you could store any address in any of the slots in the cache. And that gets really hard and expensive to build because you have to use a lot of space on your chip to hook all of your cache line address tags up to the lookup. So you say, hey, is this thing in there? You have to spend a lot of time searching for something. Whereas with this system, you can basically say, okay, I've got an A in my index spot. Now all I need to do is look at the tag at the A spot, and if it's not there, then I know I've got a miss, and if it's there, then I pull in the data that I need from that spot. One thing that some caches will do to give themselves a little bit of leeway is instead of only having one spot at each index, they'll have multiple lines that can be stored at each index, and they'll have some sort of system for replacing those things. So let's talk a little bit about some of these cache terms. So you may have heard of things like cache hits, cache misses, replacements, and thrashing. You may have just heard about them here. So a hit is when the processor says, hey, I need the data at location blah, blah, blah. So you look in your first, basically you look in your first cache, you say, is it there? If it's not, you look to the second cache, so on and so on. So a hit is when you find it, you move it back to the processor. Miss, you didn't find it, you move out to the slower, bigger levels and see if you found them. So again, replacement, if you imagine that your cache is associative and you've only got one spot for each address that has a certain bit pattern, then you need to figure out a way to say, okay, I've got another, I've read another address that fits that pattern, now I need to replace what was there with this new thing. Thrashing basically involves your memory access working in such a way that you're constantly replacing one thing with another thing, and usually you're replacing, you're basically swapping things around. So you've got two addresses that you're using in your program. They both correspond to the same tag, and so they keep overwriting each other in the cache when you go out to get them. And so there are techniques that you can use to try to minimize this. And again, having that cache that lets you store multiple things with the same index is one of the ways that you can get around this. But sometimes you'll see performance issues where, for example, if you throw a bunch of threads at something, it'll scale upward, 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 and then suddenly you hit a point where your performance drops off really quickly. And sometimes that's because you're basically getting things kicked out of the cache that are needed by the different threads and thrashing around and seriously harming your performance. So now that I've talked about caching, I'm just going to talk about virtual memory for a minute. I'm just throwing this at you because I said that I'd give a mostly true description. So in addition to having this map where you're mapping all of your accesses out to the caches in the RAM, when you actually have a program that runs in an operating system with multiple processes that are getting swapped back and forth, what your processes actually see is virtual memory. And there's actually a mapping process from virtual memory out to the RAM that then reads from the hard drive. And that's how you can actually run multiple things at the same time. But it uses some similar ideas where basically instead of having to have every single part of your program in memory at a time, you pull in pages into different frames in the RAM, and that's your working set. And so presumably most of the time what you need will be in the cache or in the RAM, and only occasionally will you have to hit disk and slow yourself down when you're trying to run a program. That was really fast. So, questions?
10 seconds.
Franco.
Do these memory spaces have the same kind of characteristics as flash memory in that they degrade over time?
You mean when we're talking about caching?
Well, yeah, is that stuff held in, like, where's it held? maybe I didn't miss the
Oh, okay, yeah. So typically these are going to be on the chip, and when you talk about a multi-core processor, each core will usually have an L1 and an L2 cache, at least modern chips, and then you'll typically find shared L3 caches or shared cache at some level. These do not degrade over time like you'd find in like you're talking about something like an SSD or something. No, these do not suffer from that same sort of problem.
So question.
Mm-hmm.
So when you say that the processor has to check L1 and then L2 and L3, so is this lookup process implemented in hardware or operating systems involved at some level?
Yes. The question is where is this lookup process implemented? As hardware and operating systems have kind of evolved together, it's usually it's split in kind of a weird way between the two. But in general, there's a piece of hardware that does most of this lookup, so that in general, the chip only has to care about an address that then gets translated into some place in each of these cache lines. A more accurate thing to say would be that usually you have to write some software that keeps track of a few higher level data structures that tell the processor a little bit about how to organize some of this stuff. That's why this is a mostly true story.
And you said L1, L2 are on-chip memories, right?
Well, okay, so in the Pentium i7, that is the case. That's not always the case. Not all processors have all of these layers of caching. So I wouldn't make a general statement that you're always going to find one in one place or one in another, but if you do have a multi-core chip, typically you will have some cache, some of your cache will be on chip and some of your cache will be shared among all of your cores.
So assuming both of them are on chip, so the difference in speed, where does that come from? Is it the size and because of the complexity of indexing that memory, or is it something else?
A lot of times it's a combination of the way that the circuits are built and also their proximity to the chip itself. So when you start talking about things that go really, really fast and are in a really small space, that proximity, even though you're talking about electrical waves propagating, that proximity becomes very important. And so it helps to have things close.
Placement on the chip, you mean?
Yeah.
Are the L's volatile like RAM?
Yes. All right, I think that's my time. Thank you.